Good morning, afternoon, for those who are all around the world. Thanks for coming along to this regular LMG Digital Power webinar. If I can just have somebody help me and let me know whether you can still hear me and whether the sound is okay, that would be great. So we should get started. So I'm pleased that you're all here and thanks for coming along. This is our first webinar. We've changed platforms from GoToWebinar to Zoom. So hopefully it works out all right. With these webinars, they occur every month at the beginning of the month or thereabouts, usually the first or second week of the month. And they cover topics around what we do, which is digital control of power electronics. So just a little bit about us. We are a company, we've been going since 2001. We have a long history of working with digital control of power electronics. Most of us have only ever really worked with digital control of power electronics. I think I once designed an analog controlled power converter. We are Xilinx Alliance program members. So that means that we focus a lot on using Xilinx products in our solutions. That doesn't mean we don't use others. At the moment, we are looking at, for a customer, looking at a TI processor. We are also using an analog devices, DSP. We have capability with systems as diverse as PICs from Microchip. We use Infineon for automotive stuff, but principally we use Xilinx technology, and a lot of the time we use Zynq because that's what we're going to talk about today. Right, about us. As I said, we're digital control and FPGA specialists. We've been working collectively with FPGAs in power electronics since 1996, where we did some hysteretic control using a very old now Xilinx chip, which at the time cost $600 and had the processing power of probably a modern Spartan 6. We're power electronics specialists. We really don't do anything else other than power electronics. So we take digital control and FPGA and we mix them with power electronics. So what's digital power? Control of power conversion using a processor or logic. Digital power, we've done systems from milliwatts to megawatts. We have worked in HVDC controls. So that's megawatts, wind turbine controllers, traction controllers for energy recovery and for traction controllers in trains. Principally, we work in the power converter part of the system. We generally don't get involved in the build out or the deployment of power converters unless there's a problem, although we often go to do commissioning. So we are true power converter people rather than application focused people. We don't have a single application focus. We do work into applications when people ask us. At the moment, we're working into grid-tied converters for energy storage. It's a common thing we've also done in the past. Power converters for hybrid and electric vehicles. So what's important in digital power? So this presentation is about what's important in digital power and why certain processes are better than others. And what's important in digital power is system latency and numeric precision and quantization and the accuracy of your compensator design. So what's system latency? Well, system latency is just the delay. How long is the delay in your processing? Delay, as I'll show in a little bit, is necessarily destabilizing. So from a feature to look for in a digital controller for a digital power system latency, having a low system latency, and then having a consistent system latency are the two things to look for. Numeric precision and quantization. This comes down to the number of bits and the dynamic range that you require. So generally, the higher the number of bits, the better. But there are some issues around quantization that mean that a high number of bits you shouldn't use if you're going to use low pass or narrowband filters. And as integrators are necessarily low pass filters and everybody needs an integrator to do control, the number of bits that you choose, the trade-off between numeric precision and quantization problems or numeric precision and coefficient quantization problems, that is not necessarily a difficult choice. Often that choice is made for you by your DSP processor or your microcontroller. But when you start to deal with FPGA fabric, you get to choose that for yourself. And so that can be a place where you can get significant advantage. And the final in this list, the accuracy of the compensator design. And I'll cover that a little bit more later. But the accuracy of the compensator design is extremely important when the converter bandwidth that you're trying to reach is high relative to the sample rate. So what does it mean, accuracy of compensator design? Well, your ability to put the poles and the zeros where you need them and thereby get the frequency response that you want. So the numeric precision and the quantization often end up that you can't accurately design a compensator or accurately design a filter. And I'll give you an example of a filter a little later in the presentation. So why is latency important? So latency equates to an ever-increasing phase delay as the frequency increases. So whenever we have a control loop, we need to make sure that the crossover frequency, that's the gain being 0 dB or a gain of 1, that we have a reasonable margin at the crossover frequency. Now, a reasonable phase margin is probably depends somewhat on what your company is using the margin for. We've seen in power supply manufacturers a margin of 65 degrees or 75 degrees. And when you see that kind of phase margin, it's clear that something has happened in the past and they've had stability problems due to the system varying, and they've fixed it by increasing the margin. Now, we've seen margins as low as 45 degrees in digitally controlled LLCs for the telco industry, and they're happy with that. But the key thing is that the delay, as you add delay, you lose phase margin. And as you lose phase margin, you lose the ability to have a wide bandwidth. So why is wide bandwidth important? Well, wide bandwidth means that you probably can reduce the number of capacitors on the output of your system. So wide bandwidth generally lowers the cost of the filter components. Okay, so latency is important because it lowers the cost of your system and it lets your controller do more. So time delay, latency. Now, it's important also to remember that latency should be constant. Varying latency is problematic. Varying latency generally leads to instability and often what looks like a bursty instability. That's where the system is stable and then it bursts into oscillation and then stops again. Why numeric precision is important? Number of effects. One effect, very small data. You can't tell the difference between a very small number and 0. And this is often the case with digital integrators, that the input gets very small and the integrator stops integrating. And this means that for the precision that you have set up with your coefficients, you have managed to make a non-zero number look like zero. And we've seen this a number of times with power converters where the system would integrate and track to the set point extremely well and then get to a short distance away from the set point and stop. Okay, so that's a really good reason why numeric precision is important. One reason. What are the effects of lower precision in filters? If you have a filter with a low bandwidth means the cutoff frequency over the sampling rate. So that's the cutoff frequency over the sampling rate. That ratio is small. So 50 or 60 hertz mains filter, a notch filter perhaps for mains rejection. If you're sampling at 100 kilohertz, has really small coefficients. And the lower precision means that the effective number of bits for these coefficients is lower. So you might have an 18-bit number, but because the number is so small, the coefficient effectively may only have 6 or 7 bits. Right, so the effect of that, if you can see this graph, is that the quantization of the coefficients can move the poles and zeros of the filter significantly. And so what we've done here as an example is we've made a filter, and the one on the left is before quantization, and that's the filter that we designed. That's where we wanted the peak. But after we implemented it with a 10-bit quantization in the coefficients, remembering that the 10-bit quantization is not due to the fact that we've only got 10 bits, it's just that the coefficients need to be very small, and so they end up in the lower 10 bits of the number. You can see that the center frequency of the notch has moved, and moved quite problematically. So this is often the case where we see digital controlled power electronic converters, and there is an instability. And what it is that the quantization of the filter coefficients, the compensator filter coefficients, has caused the poles to go outside the unit circle, and that causes instability. So not only is this a frequency precision problem, as shown in the pictures here, it can also end up being an instability. Okay, so why do we use an FPGA for digital power? The main reason is we can do things fast, and it leads to lower latency. We have the ability to sample fast and increase the bandwidth, and most of the power converter controllers that we do sample at 100 kilohertz or 200 kilohertz or 250 kilohertz, and it doesn't matter what their switching frequency is. We sample faster than the switching frequency, or at a different rate than the switching frequency. The FPGA, you have a efficient precision and quantization. You don't waste any bits. If you need an 18-bit number, you can have an 18-bit number. If you need a 24-bit number, you can have it. There's some downside to the use of high numbers of bits in FPGA, in that you end up using lots of resources, but you can manage the resource use and the effective precision. You can also run things in parallel, which is fantastic. Oftentimes the cause of poor latency or longer latency is that DSPs and microcontrollers have to run things sequentially. So as an example, we often run a positive and negative sequence controller for 3-phase systems, and we run them completely in parallel. We've also used our FPGA controller, our FPGA fabric-based controller, to do 3 different DC systems control all in one package. And the final thing is that, as you can see in the picture, digital control is all about using a delay in implementing a filter, and that delay is equivalent. The Z to the -1 is equivalent to a D-type latch. So there are lots and lots of D-type latches in FPGAs. So the mapping of control algorithms to FPGA is relatively simple. This is the control chip that mostly we use, and this is the Zynq SoC. Now the Zynq was released in 2011, so it's relatively old. There are a couple or three silicon errors in it that you need to be aware of, but most of the time it works fantastically well. And it has an A9, dual A9 core with programmable logic around it and a number of hard silicon peripherals and memory interface. And then the programmable logic lets you create your own power electronics peripherals. The pricing on this is fantastically low for those who are buying it in high volume. We've seen some amazing pricing recently for especially the bottom end, the 7010 in the low pin count package has a very low bottom price floor. So why use the Zynq? Well, it gets the low latency from the programmable logic. That all lets you do efficient precision and quantization. You can do the accurate filter designs, the accurate compensator design, and then use the processing system, that's the PS, for supervision, Ethernet, communication, human interface. You can use the programming side, processing system, for control with PL acceleration, although that's not ideal with the A9. The A9 core is not really a real-time core, and it, in terms of code sequencing and code, the ability to predict the execution time of code, there are some issues around the caching. And we've found that the MP-SoC and the ultra-scale stuff with the R5, it's the same chip, just with a different processor effectively. That is better for real-time control in the processor if you want to do that. But we would suggest you don't use real-time control in the processor, just simply do it in the programmable logic. So how do we implement the digital control? Basically, digital control algorithms are effectively serial, and the FPGA is mostly parallel. So we generate clocks, select the precision, choose the number of bits, and then create the necessary building blocks. So here are a couple of our building blocks: the space vector modulator 3. So it's a PWM space vector modulator, and that does space vector modulation or digital control for three-phase systems, and it does it with precision compensation and with dead time compensation as well. So it has all those features built into it. And effectively, by changing the parameters on the that we send to the blocks, we can change the period, the switching frequency, the dead time, all of that as the system is running. So all of that is locked into the block. And then we have a relatively simple block in AB to DQ. So we link the blocks together. All of those blocks are individually verified. These blocks we run in the Zynq programmable logic or in any other FPGA. So how do we deal with the serial nature of the control system? Basically, we use state machines, and we can't pipeline. Pipelining is good, but you can't because the latency would be catastrophic. So here is one of the things that FPGAs are very good at, pipelining, and we don't use it. Best action in parallel and pipeline what you can. Okay, so what we found, and this is a good sort of tip, for power electronics control, we don't clock our fabric much above 100 megahertz. I think at the moment we have a couple of controllers running at 250 meg, but what this lets us do is it lets us get things into the fabric relatively easily. We don't generally then have much problem of timing closure. We also run the clock rate at much greater than the sampling rate, and this reduces the latency as much as possible. And a good thing to remember about digital power is you don't need to wait to apply control action. You should apply control action as soon as you're ready. So minimize the latency, even though you have even if your sampling rate is low. Okay, so we just generate a sample rate tick. We generally use either the external ADC or the sample rate is generated internally. But important point, the sampling rate for your control does not need to be the same as the switching frequency, and much faster than similar systems running in microcontrollers. So typically for grid-tied inverters on a TI DSP, you might switch and sample at 30 kilohertz. We would switch at 30 kilohertz and sample possibly at 300 or 250 kilohertz. So we sample much faster than we switch. And that is something that if you are using FPGAs or the Zynq, that is very much worth doing. So the Zynq has a DSP48E, which is a 24 by 18-bit multiplier. When you're using the Zynq, you need to be aware of your utilization. Good combinations are 18-bit data, 25-bit coefficients, and we have an IP block which can implement a large number of filters using the same or set of multipliers. So that's a filter block that we use to minimize the multiplier use. How many bits do you need? Well, for power electronics, we have always felt that 16 was too few and that 32 bits is a bit of an overkill, especially because of the way that the coefficient quantization happens. So we can have different precision for different variables. So we often have, especially if we're doing grid tied and have recursive repetitive filters, that they'll be quite low precision, quite a low number of bits. But what we generally use is we use the native 18 on the Zynq. So we use 18-bit binary numbers and 25-bit or 35-bit coefficients. If you have a different size DSP block, different width, then use that as your base number of bits. The Xilinx tools do this thing called inference, where you can infer DSP blocks. So this code here will, when you build it, it should infer a DSP48E. And if you are looking to infer it, you can see the code down the bottom where it does the multiplication. You can see that it's arranged in a way to attempt to infer a DSP48E. And here is the Xilinx tool confirming that that has happened. For a 35-bit to 25-bit multiplier, we've ended up using 2 DSP blocks. Okay, which language to use? Any hardware definition language will do. We use VHDL. And we also use high-level synthesis. So get FPGA code from C. It's a little disconcerting when it happens. And then the software-defined system on a chip, the SDSoC environment that uses HLS. So basically, you can write C and it will turn it into FPGA code and then synthesize it for you. It all gets a bit far away from feeling completely verifiable to me. So we use HLS minimally in algorithm design. Other ways to code FPGAs, code the Zynq, include using MATLAB Simulink and using the FPGA coder, but we don't do that simply because we do not feel that we have enough testing control. Which building blocks you will need for power electronics? You'll need a PLL, 3-phase transforms, IIR filter block. So we have all those and they're available as licensable IP. If you're interested in FPGA IP licensing from us, then you can send me an email after the presentation. Happy to talk through that and how it works. And then we build a sequencer that just basically sequences the blocks one after the other so that closing the timing in the FPGA is relatively simple. Okay, just a quick case study on how we implement IIR filters. Big piece of the compensator. So we use a bi-quad form for computational efficiency, precision management. A couple of forms. Most of the best filters have internal clipping, so they clip externally before they clip internally, and the DF2 forms are good for that. But there are reasons that you might want to use the direct form 1 or the direct form transform 1. Just an introduction to the delta operator. Very good for filters with low bandwidth, such as resonant peaks. And there's a reference on the bottom for how to design delta filters. So the delta filter, if you want a delta filter, this is how you can design them. Use a DFT transpose form, and then you can design a module which works for both Z and delta filters with a single parameter. And this is a really, really useful thing. We have a filter block which you can switch from a straight Z transform to a delta transform. Creating the IR filter in logic. So that's the block there, and there's the pseudocode. The logic steps for using the Zynq: decide what can be paralleled, then pipelined, design the sequence of events you need, and create a finite state machine. And that's the finite state machine which runs our IR filter block. So it reduces it to a very, very simple sequence. Makes use of all the Zynq's hard silicon and features, and runs extremely quickly. Okay, how to use the Zynq's PS. So that's the processor. Two options. One is a supervisor and a calculator, and we know people who are doing that. There are a number of large industrial control power electronics people who use the control code in the processor and have peripherals in the fabric, and the other alternate is purely as a supervisor, and that's what we do. So we always use an RTOS. On the processor, we've used free RTOS, do a really good job, and now supported by Amazon. So that's a good free product. We also in the past have used Microem, the Microcos 3 from Microem, and that's a really, really nice product, but proprietary. So the key thing about the processor, it's not as fast as the logic. So we use it as a supervisor when we run Linux. It's not real time. Any decisions are made in the logic or in the real-time operating system. Linux is fantastic. As soon as you put Linux on, you get all kinds of fantastic opportunities for scripting. On our control platform, on the Zynq, we run Python. So all the support functions that we need are available in Python on the actual platform, so you can develop on the Zynq. We use custom device drivers. We have a device driver for each IP block, and if using the processor as a supervisor, use Linux on both cores, so there are dual A9s. Otherwise, use Linux on one and an RTOS on the other. I think that is a good idea. There is an issue with the Zynq that the caches can mess with getting consistent and fast processing on the cores. So we have avoided using the cores for real-time control. And this is an internet-connected application that we run on PCs that connects into the fabric via the Linux. This is streaming over gigabit Ethernet. This is data from the programmable logic moved into the Linux via a kernel driver, and then from the kernel space to the user space, and then pretty much streamed out through gigabit Ethernet. We can do decimation on the stream so that we don't get all the data. The data comes very quickly and often overwhelms PCs. And the scope utility, this, what we call our control scope, runs in Python. And if you want to, you can check out the YouTube video of it working on our YouTube channel. Right, so thanks for attending the webinar. Does anyone have any questions? Any questions? So quick question, what's the scope utility? So this one here, this is where it's a program. It runs on Windows on Windows 7 and Windows 10. It's proprietary to us, and it performs a scope function. Okay, great. Okay, so I got a question from the trade-off about bits, whether more bits is always better. So if you have more bits and you make a filter, then the coefficients necessarily have more bits as well. But depending on what your sampling rate is, the coefficients can be very small. So if you have 18 bits and you have a multiplier that suits 18 bits, then adding more bits will use up more multipliers. So more multipliers means more fabric, means more cost. So first thing is you have to choose the number of bits that are right for your application so you don't have too many. Obviously, nobody in any digital system really ever chooses to have more bits than they need. So that's the first part of it. If you sample faster, then the size of your coefficients gets smaller. So you increase the number of bits or decrease the number of bits and sample faster, then you end up with quantization problems as you make low pass filters because the coefficients are very small. And if you look at how that happens when you increase the number of bits, the combined with sampling rate, you end up that adding more bits isn't necessarily going to do you any good. Okay, question. Are you using the core? Yeah, the PS is the core. The processing system is the core. We use it for logging, communications, monitoring, non-real time. So it's not real time. And we use Linux and we run it across most of the time we run it across both cores, but we sometimes run RTOS and RTOS on the other one. Okay, Luca, you can't use a high safety integrity free RTOS or an RTOS on the A9 and have it high safety integrity. So the processor itself isn't. If you're using the R5, then the use of I think FreeRTOS has been submitted a number of times to third parties, and I think Amazon are pushing it that way. So how, from a high reliability point of view, say if you wanted to use it in an airplane, then simply put it through that audit process. I'm not entirely sure that I have answered your question. If I haven't, please let me know. Okay. Question: when defining precisions and designs of feedback, how do you deal with potential overflows and getting rid of extra? Okay. So there are a number of ways that we deal with filter overflows. Choosing the right form is important. So with the DFT2, it is guaranteed to have external clipping overflow before the internals are clipping. So this is one of the reasons why you need to choose exactly the right filter form. Now, in terms of filter design, once we've chosen the form, and we have a number of different forms pre-implemented in our IP library, then we design the coefficients, and with the coefficients and the code, so effectively the coefficients in whatever code it's running, we then have a complete verification test sequence for filters where we confirm operation. So if it's a filter that's implemented to be implemented in FPGA fabric, we do that all with the test bench. So we have UVVM test benches, which can basically determine the frequency response of a filter. We have all of that, and then generally they get tested in the fabric as well. They get tested in the fabric by simply with a in fabric test harness, which we can test any filter at any time. So we also have in our IP blocks, we have a DFT block, so we can do a DFT on any system block or any power converter. So all of those steps for all the filter with the coefficients. So if you change the coefficients, you have to redo all of the verification steps. We also have recently added some dual tone tests to look for intermod products. We added those, yeah. And most of that is done, most of the initial design proving, I guess you could say, is done with the test bench in a RTL simulator. So would I remember, I recommend to use core for control? Absolutely not, no. In terms of latency, you're always going to be losing. There's absolutely no reason to. The only reason that I would recommend it is if you've got a large software team who really like writing software and they are so resistant to using RTL that you can't afford to get rid of them. So definitely not use the core for control. Probably even with the R5, we wouldn't use a core for control. We've found that the safety certifiers for programmable systems like FPGAs a lot more than they like software. Anything sequential is problematic for them. Do you use any fixed point library or package for MATLAB before coding RTL and FPGA? So in terms of simulating this stuff, we have existing code. So all of our FPGA code is existing. It's in IP blocks. So most of the time, most of what we do, we don't change it. And most of the time, the reason for that is for the certifier, that most of the certifiers in the world have seen most of our code. So that it gives us a huge advantage. So we try not to change the code. Or if we do, we include them in the disclosure. So in terms of simulating, we have some simulation models that we can run in Simulink, but mostly with fixed point. We can, the fixed point effects in power electronics control are typically located in one place in the system. And so what we have found is that if you want to do what is the effect of a fixed point limited number of bits, you don't need to do that throughout the entire system. You only need to look at it in one place. So we have, I guess, a lot of experience in simulating power electronics and FPGA control and knowing where the quantization will have an effect, where the limited number of bits. And generally, everybody knows that the most imprecise place is in the A to Ds. Now, do we have a fixed point library that we run for our simulation? Yes, we do. We have a simulation test library, UVVM stuff that we use constantly to do all of this verification. And we treat filter design as a verification problem. Okay, so a question, how does the crossover frequency in digital control compare with that in analog control? Right, now this is, if you're only interested in crossover, then there are a couple of things that you need to consider. If you're only interested in crossover, then you're probably only interested in reducing the size of your output component, because that's why you want high crossover. So if you're interested in crossover just for the sake of crossover being higher, then you can get the same crossover in digital as in analog. Now, everybody says you can't. And everybody says that basically because the delay in digital is a sample, you're going to get worse bandwidth. The delay in digital doesn't need to be a sample. So you can process faster and get output out of your controller faster. Now, lots and lots of silicon-based controllers can't do that. And so there's this kind of feeling in the digital control world that you sample at one instant, do your control calculation, and when you're next sampling, you apply your control action. Now, that makes no sense. So sample, and as soon as you've calculated, apply the control action. And you'll be able to get significantly higher bandwidth than you think. Now, some of the highest bandwidth controllers in silicon are digital. They look analog, but they're not. They're all done digitally internally. And that's one of the big trends that's going on, is that you have these chips and they're completely digital, but you set them up using a resistor network on the outside. You have a pin that has 3 functions, right? It's effectively an analog pin doing a digital function internally. Right? Lots and lots of control for power, low power, is now quite digital. Lots and lots of it is done in VHDL. Okay, more questions. So, Kalind, the answer is it'll be the same if you want it to be. Okay, and the question, do you model the plant directly in the Z domain or convert? And the answer is neither. Do I model it in the Z domain or in the S domain? No. It's almost impossible to model a continuous system like power electronics, which is switching, and most power electronic converters have states that disappear and reappear. If you don't know which ones those are the snubber voltages. When you close the switch, the snubber voltage state goes away. So I give another presentation on frequency responses in control. We measure frequency responses of power converters. We measure them on the power converter. Sometimes we measure them on a model, but most of the time we measure them on the power converter, because power converter models take a long time to get accurate when compared with the ability to rapidly and repeatedly do power converter transfer measurements. So no, we don't do it in the S domain, and we don't do it in the Z domain. We do it in the frequency domain. Yeah. If you were to look at what we do mathematically from a modeling point of view, probably closest to something like a modified Z. So power electronics doesn't really use the Z transform, even though it seems like it might. The modified Z, modified Z is a way of looking at continuous systems and digital systems together at the same time. So if you imagine you're sampling the digital system, you've got one sample, you have an output, and you hold that output. The analog system reacts to that output and changes during the samples, and the behavior during that sample period isn't generally able to be accurately represented by a Z transform. And it's actually not accurately, you actually can't really accurately represent it by an S transform with integer powers. But that's flexible structures are a really good place to look if you're looking for modeling for power converters. Final thing about it, by the time that you have modeled your power converter, you could have measured all of the transfers that you need to do the control design. So we're very much about measurement now. Okay, I think I've answered all the questions. If any of you want to talk for 20 minutes, you can email me. I've got a list of all of the people who've attended. So if you have an issue that you would like to talk to me about in the next week, it has to be either the end of this week or in a week's time, because I'm going to Belgium for next week. If you have any questions, you want to talk for 20 minutes, you have my email address, and we can have a quick Zoom conversation about what you're doing. So that's limited to the first 7 people who email me. So if you have an issue you want to discuss and see whether we could help with, first 20 minutes, freebie or consultation, send me an email. All right. That's the end of this presentation. Thanks for coming. I've just got one more chat to check. There's a comment that says that Zynq are expensive. From Vladimir, yes, Vladimir, they're extremely expensive, except if you buy them. So as I said, the pricing on the Zynq that we have seen for customers who have good accounts with Xilinx, the pricing that we've seen for large numbers of buying Zynq are amazing as to how low that price is now. So if you're having trouble with pricing on Zynq, then you can try the 7 series. We have good success with 7 series. I don't even know what the list price is for one-off on Zynq anymore. We don't buy that way anymore. So yeah, being Xilinx Alliance partners, we get relatively fantastic pricing. But if you want to make use of that pricing on our pricing on Zynqs, we can look at that too, whether we buy them and then sell them to you. They're a really good value, surprisingly. Now, Xilinx 7 series is a very good chip. The Xilinx Spartan 6 is still fantastic. We still make things with Spartan 6, still design Spartan 6, even though we shouldn't. All right. Thanks. No, you're welcome. Yep, you're all welcome. As I say, first 7, if you send me an email, we can have a 20-minute conversation about what it is you need. First 7. All right. Talk to you all next month. See you, bye.